welcome back. This is another install of chapter 1. This is part B. It's all about understanding the mole and how to calculate the amount of substance using a mole, which is a chemistry unit and something you will be very familiar with now and in the future. So, in science, you use different units. You have customary units, feet, inches, yards, miles, and metric units, which are a little easier because they work in base 10 with a kilometer, meter, centimeters, milligram, liter, and whatnot. So that's understanding the dimensional analysis of converting units. If 1 foot equals 12 inches, or we could say 1 foot per 12 inches, is the same thing as 1 foot equals 12 inches. So what we use in chemistry are different units, particularly it revolves around the mole. So we'll talk about Avogadro's number, which is 6.022 times 10 to the 23, and it's basically just a unit used just like we would use for dozen. So if dozen equals 12, a mole equals 6.022 times 10 to the 23. Also, a mole, when you're dealing with mass, is molar mass. So 1 mole of hydrogen atom would weigh 1.008 grams. If you had hydrogen molecular, which is H2, it would weigh 2.016 grams for 1 mole. Notice it's double, obviously, because there's H2. Also, concentration we will work with a lot. We use molarity or molar. It's the same thing as saying 0.100 molar is 0.100 mole for every 1 liter. And concentration varies depending on how concentrated something is. We also use decimeters cubed commonly here in the AICE course instead of liters. So why do we have a mole? We know an atom is very, 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 very small. So it's basically weighing nothing compared to things around us. So we use a mole to help use that scale to help come with that small mass. So what number relates moles to very small things like atoms? And that is Avogadro's number. Avogadro is an Italian scientist who basically through experimentation came up with a mole to be 6.022 times 10 to the 23 of whatever. It could be anything. Just like a dozen, 1 dozen equals 12 whatever. So if you had a dozen cookies, 12 cookies. A dozen pencils, 12 pencils. So a mole of atoms would have 6.022 times 10 to the 23 atoms in that substance. If you had a mole of molecules, same thing. It would be 6.022 times 10 to the 23 molecules. And so forth with particles, same thing. Formula units, same thing. Anything really, if you had a mole of substance, mole of something, it would be 6.022 times 10 to the 23 of those somethings. So if I had a mole of sodium atoms, it would be 6.022 times 10 to the 23 atoms. Same thing, if I had a mole of fluorine, it would be 6.022 times 10 to the 23 atoms. If I had a mole of sodium chloride, again, 6.022 times 10 to the 23 formula units. Now, we use formula units because it's an ionic compound. We can't use atoms because sodium chloride is not an atom. We look at mass, how we relate mass with moles. If I had a mole of sodium atoms, it would be 23 grams per mole. Same thing with fluorine. If I had a mole of fluorine, I look up the periodic table. Fluorine weighs 19 grams for every 1 mole, so per mole. And if I had sodium chloride, add up sodium, add up chlorine, you get 58.5 grams for every 1 mole. So a mole of sodium, 6.022 times 10 to the 23 atoms. If I had a mole of NaCl, it would be that same number, 6.02 times 10 to the 23 units. Now if I separate sodium chloride I would still get 6.02 times 10 to the 23 ions of sodium. So I'm just separating the sodium from chlorine, and the same thing for chlorine because it's both a 1-to-1 ratio. So 1 unit is made up of a sodium ion and a chlorine ion. If I had a molecule of sodium chloride, there's 1 ion of sodium. Same thing, there's 1 ion of chlorine. Okay, so you have to distinguish between a molecule and an ion. So you separate the molecule from its ion, or ions from its molecule. Now the other thing that comes up is atoms versus molecules of diatomics. So if I had chlorine atom, that's a single atom, it would be 6.02 times 10 to the 23 atoms. Now if I had a mole of chlorine molecules, the molecule is made up twice as much. So that's why it's 1.2 times 10 to the 24. So it's twice as much of the 6.02 number. Because chlorine is diatomic. It's one of the 7 diatomic elements that you need to know. So showing the math, basically you have 2 times the 6.02 times 10 to the 23 number. Here's a little map to help you. You can see moles is in the center because, again, it's a very important unit to understand. And then you use Avogadro's number if you had something like molecules, formula units, atoms. And then to the right of that you have grams. That's when you use the molar mass. You have to distinguish if you're going to look for mass or not. And then if you're looking for volume, we have another constant depending if you're at STP or RTP. One is standard temperature pressure and one is room temperature and pressure. That basically the difference is 0 degrees is standard, 25 degrees Celsius is R, room. Okay, so if we have atoms in the moles, we use Avogadro's number, which is 6.02 times 10 to the 23. If we're going to mass, we use molar mass, which is, for example, carbon is 12.011 grams for every 1 mole. Again, that comes from the periodic table. Another unit that we are going to work with later on is concentration. Again, we talked about this earlier. 0.100 molar or molarity is the same thing as writing 0.100 moles per decimeter cubed or liter, which is also the same thing as writing it as a conversion factor of 0.100 moles equals 1 decimeter cubed. So the per is just another way to write a conversion factor. Okay, so here's some practice problems converting mass to moles. We had 10.7 grams of sulfur. Okay, that's your starting point. Anytime you're doing dimensional analysis, that's your given. You draw your T-box. We look up the molar mass of sulfur because we're dealing with mass, grams, mass. So we're not using Avogadro's number. And for 1 mole of sulfur is the mass of 32 grams. Grams cancel out, and you're left with 0.335 moles of sulfur. Alright, now we have sulfur molecule, which is S8. It has 8 atoms around bonded to each other. We have 64.2 grams of it. Now the difference here is that you have 8 sulfur atoms, so the molar mass changes from 32 to 256. Again, but it's 1 mole. Grams cancel, and you're left with a 1/4 mole of S8.250. Here we got 60.45 grams of iron 3 nitrate, FeNO3. That's your given. Then you have to look up the molar mass of iron 3 nitrate, which is about 241.86 grams. Again, you're dealing with mass, so you use molar mass. And you have 1 mole of FeNO3 for every 241 grams. Grams cancel, and you're left with 0.250 moles of FeNO3. Calculate the amount of atoms, tricky, atoms of 7.10 grams of chlorine atoms. So right away, you're thinking atom, you gotta think Avogadro's number, but also you're given mass. So it's a little more steps involved. You start with your given. Anytime you're dealing with mass, you always use molar mass. So since we're dealing with an atom of chlorine, it's just going to be 35.45 grams, which again, look on the periodic table, is for 1 mole. Grams cancel. Now we're at moles, we want to get to atoms, so we're not done yet. So we need moles across from chlorine. We need atoms, which is again Avogadro's number, which is 6.022 times 10 to the 23 atoms of chlorine. Moles cancel, and you're left with 1.21 times 10 to the 23 atoms of chlorine. Alright, so you want to work these 3 problems out as practice. You can check your answers, A, B, and C. If you have any questions, you can always contact me or a fellow classmate. And that's it for part B.